Okay, it's 6 o'clock here in the UK. Good evening, everyone. If you're joining from UK, and good day if you're with us from other parts of the world. My name is Human Takhtichian, and I'm the current ICorr Aberdeen branch. Welcome to our first technical program of 2022, which is a joint event with Energy Institute. Today in the panel, we have Dan Byrne, Vice Chair of Energy Institute Aberdeen Highlands and Island Branch. And he will give us a short presentation about the Energy Institute activities after this. Please note that this webinar is recorded and will be available as usual on our YouTube channel. Also, please note that if you have any question from our presenter today, you can ask it in the Q&A section below. Don't ask please in the chat box because it might be lost or missed. Please put them in the Q&A session. So Dr. Oli, our ICorr Aberdeen Vice Chair, he will go through them after the presentation is done. So as you have already seen in today's event flyer, today's presentation is by Dr. Joshua Owen from University of Leeds. The topic is Advanced One-Screw Flow Cell methodology for validation of a new stage inhibition approach for matrix acidizing treatment. This is a joint industry project with Schlumberger. He's joining us from France, I guess, with his supervisor, Dr. Richard Baker, Associate Professor in Corrosion Science and Engineering at University of Leeds, and Evgeny Barmatov from Schlumberger Cambridge Research. But before I invite our speaker today for his presentation, I would like to give you a brief summary of ICorr Aberdeen upcoming programs. First of all, I would like to thank all our branch sponsors who have kindly supported us regularly. This has enabled us to keep all our monthly meetings happening without any gap for the last several years. Really appreciate that. Also, I would like to thank Aberdeen branch committee members who have all supported branch in arranging all the events throughout the year. Please note that all of the previous presentation slides, including question and answer, are all available on our website. And last year recordings are also on the YouTube channel, so you can explore the previous recordings on our YouTube channel. The program for the 2021-2022, the continuation of the program from January, that's on the screen. You probably have received them by email when you have received the invitation for this webinar. If you haven't, you can just go to the ICorr website and see the event program and the future events to register for. So we continue our program from February with still our Zoom events and March as well. But we are planning to have April and May program, which are the last two programs of the events of the year, face-to-face in Aberdeen. And one more thing, but just a reminder before I go through the Young Engineer program, we soon will launch our call for speakers. You will receive an announcement for the 2022-2023 technical presentation. So you can either wait to receive the announcement or just, if you are interested, mention about your interest in the survey that you will have after this webinar on Zoom. So just put your name, email address, and the topic that you want to present. So we will contact you. So the opportunity for webinars or in-person presentations in Aberdeen, if you're interested. So the last thing before I hand it over to Energy Institute for the introduction, this is just an introduction about the Young Engineer Program 2022 that we will start after tomorrow, our session, for the first time in Aberdeen. I have mentioned about this in the previous webinars, but we actually are launching this now with 23 applicants, which are selected from 50 applications that we received, and they were carefully selected by 6 evaluators within the committee. We will have this program until November, and in November there will be a competition for between these applicants, and then hopefully we will have a winning group which we will send to NACE conference in 2023. So if you are interested in the future programs and you think you meet the criteria of a young engineer, you can contact us. Probably the next one that will be launched in 2024 will be in London. If you are based in London or you can travel to London, keep in mind that you can apply for that next year. Yeah, so that was just a brief introduction about our upcoming events. And with that, I will pass it to Dan for his presentation. Let me put the slides on. Yep.
Okay, thanks for that. And again, good evening to you all, and thank you again just for taking the time to join us on this Burns Night in Scotland for this joint Institute of Corrosion and Energy Institute presentation. My name is Dan Byrne. In addition to my day job as an Integrated Services Manager for Taurus BGP, I'm also the Vice Chair of the Aberdeen Highlands and Islands branch of the Energy Institute, as Hughes said. It's a real privilege to be with you, and I think it's great to have the opportunity to share some additional details really about our local branch of the Institute before we really get into the meat, or perhaps that should be the haggis of tonight's presentation. So at a local level, we have a very interesting, varied and exciting technical programme, and it's already taking shape for 2022. But, you know, similarly to the ICorr Institute of Corrosion, all of this would not be possible without the incredible support of both our regional membership and our branch partners. And in this case, for the Energy Institute, it's Bilfinger UK and Imbrand. Obviously, pandemic constraints still has limitations into how we've been delivering through the course of the year, but we're hoping to be more face-to-face with many of our events going forward this year. So please just take time to maybe regularly visit our web pages to see what's on and, you know, how that will be delivered. But also, please don't hesitate to reach out to us if you'd like to volunteer any interesting topics, really for broader share with our membership and the wider energy sector as a large. And of course, I'd encourage everyone to please continue to support these types of events through your attendance. Definitely for these local branches, our membership most definitely makes us. One thing I did want to highlight was our annual branch dinner here, and that's going to be scheduled to be held on the 12th of May at Aberdeen's Marcliffe Hotel. And this is this year one of our key charity recipients of our fundraising efforts is the Pound for Piper Trust, and that's a charity that's responsible for the upkeep of the Piper Alpha Memorial and Remembrance Gardens here in Aberdeen. In addition to my role within the local branch of the Energy Institute, I'm also very honoured to be one of the trustees for Pound for Piper. So I'm obviously hoping that our dinner is a resounding success in raising much needed funds to support our wonderful charity. So if any of you attending tonight would like to book a table, maybe sponsor part or all of our event, or even supply an auction or a raffle prize to help us raise funds for all of our nominated charities, then please reach out to us at our email address of aberdeen@energyins.org. Maybe just move to the next slide, please. Okay, I just wanted to share just this last slide, really thinking about what are the tangible benefits to joining the Energy Institute, and particularly in being active with local branch. And one of the major benefits is not least the opportunity to engage with like-minded professionals working across the whole energy sector. Of course, professional membership and accreditation is an important part of the Energy Institute's offering, and our two highly experienced local branch membership advisors, Yvonne and Alison, they're available to assist you in your own development journey, so please do not hesitate to reach out to discuss your needs. Of course, there are other benefits of membership, including access to our EI Connect programme, and this encourages and facilitates two-way mentoring opportunities, as well as the access to our EI Enable programme, which provides the wider EI community with free and confidential advice and support. And that's both professional and personal. Like the Institute of Corrosion, here at the Energy Institute, we both value and listen to our membership. So please reach out, engage with us, let us know what you want to see and hear more of, especially at this local level. And just share your thoughts with us via, again, our email address at aberdeen@energyins.org. So thank you for listening to me this last few minutes. And I think maybe in the immortal words of Robert Burns, now's the day and now's the hour. So please enjoy tonight's presentation. Thank you.
Thank you very much, Dan. Okay. So back to this evening topic. Let me stop sharing from my side. Okay. So let me introduce our presenter today, Dr. Joshua Owen. He's a research fellow in the School of Mechanical Engineering, University of Leeds, with expertise in corrosion in aqueous CO2 environment and electrochemical flow cell design. He has a PhD in mechanical engineering from the University of Leeds, completing his thesis entitled Erosion Corrosion of Carbon Steel in Complex Flow Geometrics in Oil and Gas CO2 Environments, collaborating with Shell UK to enhance mechanistic understanding of carbon steel degradation in sand-laden corrosion fluids. Joshua has numerous publications in the field of corrosion and has worked with multiple industrial partners in the oil and gas industry. This project was completed as part of an EPSRC-funded Impact Acceleration Account, supervised by Dr. Richard Barker, Associate Professor in Corrosion Science and Engineering at University of Leeds, and Trevor Hughes and Evgeny Barmatov from Schlumberger Cambridge Research. Schlumberger is a world-leading oilfield service provider. Before Joshua starts his talk, there is a poll related to his talk that I will like to run for a minute. Please choose your answers, and then Joshua will start presentation based on that. So I'm launching the poll just now. Let me know if you see that. Yep. We have received answers from 20 people, from 34 participants. I'll give it another 5 seconds. Okay. Thank you. And I share the results. Shows that 13% of people, they have selected yes. So the question was, do you have experience of using flow cells for corrosion experiments? 13% yes. 33% familiar with the method, but they don't have the experience, and 54% are not familiar with this topic. Okay, Joshua, please, you want to share your screen?
Yeah, sure.
Cheers, thank you.
Okay, is that okay? Can you see that?
Yes, perfect.
All good. Okay, yeah, thanks very much for the introduction, and thanks everyone for joining. So yeah, that poll is quite useful. So I guess roughly half of you have kind of had an experience of flow cells, and the other half have not really got any experience of really what they are. So I'll go through those kind of the main sort of ideas of flow cells, but essentially a flow cell is a very useful sort of technique that we use in, well, not just in corrosion research, but in obviously of interest tonight is how we use it for corrosion research, where you can essentially get a very sort of controllable conditions for high precision experiments. And it offers a number of advantages over some more traditional experiments where you might just immerse a sample in a sort of corrosive environment and do some measurements. And I'll go through a little bit about our design that we've used for this particular application, which is for matrix acidizing treatments and evaluating a stage inhibition approach is what we call it. And this is an approach that is designed or developed by Schlumberger. And what we wanted to do working together was essentially use our flow cell methodology, which we have at the University of Leeds, and combine that with the sort of expertise of the methods that have been developed by Schlumberger to essentially validate the inhibition approach, with a particular focus on matrix acidizing treatments. So again, that may be familiar to some of you. And I'll go through sort of the main challenges that you see in a matrix acidizing environment. So just to give an overview of essentially what I'm going to be talking about for the next 25, 30 minutes or so. I'll give you a little bit of background, like I said, on matrix acidizing and acid corrosion inhibitors and why they are essential and how effective they are in a high strength acid environment. I'll introduce the staged inhibition concept. So where this idea sort of came from and the motivation for the study, how it's been evaluated prior to the work we've done at the university. And then I'll go through the sort of methods that we've developed at the university where we can use the 1-3 flow cell to actually evaluate the inhibitor approach, essentially with the idea of giving it a little bit more sort of validity before Schlumberger can use this technique in the field. And I'll also show you the main results and the significance of sort of different parameters that have influenced the results that we get. So as said, there's a few sort of our contributors and authors of this work. They've sort of mainly been introduced now, but we've got Trevor Hughes from Schlumberger, who's now retired, but he's a scientific advisor with Schlumberger, and Evgeny Barmatov, also from Schlumberger, he's principal research scientist there. So it's Schlumberger Cambridge Research. So Trevor and Evgeny essentially over a number of years developed this idea. And then at the university, my supervisor is Richard Barker, who's an associate professor at the university. Our expertise is in corrosion and some energy applications, and we have developed flow cells over a number of years. So we've kind of worked with Schlumberger on quite a number of projects now, still ongoing, working in different sort of areas, solving some of the main sort of corrosion challenges and inhibition challenges through sort of collaborative research, through PhD projects, and through the project that I completed around about 18 months ago. So to give an introduction, I'll change my pointer. Schlumberger prepared a sort of brief video. It's about 20 seconds long, which gives a bit of an idea of matrix acidizing for those that aren't familiar with it. So I'm going to play this now. Hopefully everyone can hear it okay. And this will kind of give you a little bit of an introduction to matrix acidizing and some of the main challenges that are faced in terms of corrosion.
The simple purpose of matrix acidizing of carbonates is to increase hydrocarbon production. Matrix acidizing involves the injection of strong hydrochloric acid solution into the formations below fracturing pressure to remove formation damage introduced during drilling or to increase permeability. The acid reacts with rock minerals to create wormholes and increases drainage area. Coiled tubing service is used to inject acidizing fluids directly into target formations to minimize exposure of wellbore casing and completions hardware. It is essential to employ acid corrosion inhibitors to minimize corrosion of metals in the wellbore.
Okay, so hopefully everyone heard that okay. So that gives you a little bit of an idea of the purpose of matrix acidizing, essentially to kind of maximize production. But inevitably, the environment that we've got comes with certain corrosion challenges, obviously. So typically, it's a highly corrosive fluid that would be injected into the well. Normally, high strength hydrochloric acid, and temperatures can be extremely high, obviously depending on the conditions within the well. The injection periods normally last for about 3 to 6 hours, so that'd be the period over which the hydrochloric acid is injected. So obviously during that time, that's a particularly sensitive period where corrosion can be extreme if it's unmitigated. But you also get an additional sort of flow back period after the injection period, which is essentially where the unspent acid within that's been used in that procedure will essentially flow back into the well over the next couple of days, and then essentially that would make the kind of the fluid environment more corrosive because you've still got some of the acid remaining in there. So for the purpose of what I'm presenting today, we're just looking at the injection period, but we've done some work in the past with Schlumberger looking at using the flow cell to evaluate flow back as well, if that's of interest to anybody. But today, just focusing mainly on the injection period. So inevitably, when you've got these highly corrosive fluids coming into contact with all the materials in that environment, and that can lead to some pretty high corrosion rates. So essentially, our main corrosion challenges, so like I said, very high strength hydrochloric acid. And just to give you an idea of the corrosion rates that we can get in some cases with an uninhibited carbon steel at the temperatures that would be relevant, corrosion rates can be around 1,000 millimeters per year. So it's huge corrosion rates without the application of a corrosion inhibitor. So obviously, applying an inhibitor is essential. And in this particular case, we would use acid corrosion inhibitors, which are corrosion inhibitors that are ideally suited to the acidic environment. And they're usually required in very high concentrations just to maintain acceptable corrosion rates. Various components are affected in the process. So obviously you have to deliver the hydrochloric acid into the well. And that would be done through carbon steel coiled tubing normally. And obviously the wellbore casing and the materials sort of surrounding the area where the acid is injected are also exposed, and that can lead to various corrosion challenges. You've got different materials in there, and all of those materials obviously need to be protected from the corrosive environment. And as I said, once you've completed this procedure, you can also have a flowback period. and that can impact on various other aspects of the infrastructure, essentially. To conclude, overall, it's a very corrosive environment, as you can imagine when you're using such a high-strength hydrochloric acid. So acid corrosion inhibitors, like I said, are essential. And corrosion inhibitors generally classify in a few different ways, depending on how they interact with the surface and the mechanism of inhibition they provide. So there's physisorbed inhibitors, which would be some sort of electrostatic interaction between the inhibitor molecule and the carbon steel surface. Chemisorbed inhibitors, with this electron transfer between the inhibitor and the metal. And then finally, polymerizable inhibitors. So this is when the inhibitor adsorbs to the surface, it forms a film, and it polymerizes in the environment that it's in, essentially establishing that film, strengthening that film, and it becomes a more protective corrosion inhibitor. And propargyl alcohol is an example of one of those inhibitors. Polymerizable inhibitors, therefore, because of the acidic environment, and acidity would promote the polymerization process in this case. The polymerizable inhibitors are favored for protection of carbon steel and matrix acidizing operations. So based on the kind of fundamental nature of those inhibitors and how they form a film and how they would polymerize, that is essentially what has led to the development of what Schlumberger we're calling the staged approach. But initially, just looking at how the inhibitors perform, just to give you an idea of how effective these inhibitors can be. So this is some measurements of corrosion rates of carbon steel immersed in different strengths of hydrochloric acid with various concentrations of propargyl alcohol at 80 degrees C. And what plotted here is the inhibition efficiency as a function of these different concentrations. So you can see, bearing in mind that we had corrosion rates without an inhibitor in terms of the order of 1,000 millimeters per year, we can still get 98, 99% efficiency, provided there's a sufficient amount of corrosion inhibitor added in this environment. So they're incredibly good at protecting steel surfaces from in the high strength hydrochloric acid environment. And this particular test is just for propargyl alcohol, which essentially is quite a basic inhibitor. There's no sort of additives in that system, so there's potential to improve those inhibitors depending on the kind of chemical blend that's used and developed by Schlumberger. So they can be very, very effective. But what Schlumberger kind of had learned was that they can maintain this efficiency by reducing the corrosion inhibitor concentration once the film has been formed. So it kind of lists the question is like, how effective could that be? Can you significantly reduce the concentration and maintain a protective film once the film is formed, based on how the inhibitor adsorbs to the surface and how it will polymerize on that mechanism of inhibition? So what the staged approach is essentially a two-stage process where during the film forming stage, stage one, the inhibitor will be added in high concentrations, allowing the persistent film to be formed. The inhibitor concentration would then be dropped, and that would maintain the film. So the idea being that the lower concentration of inhibitor is required to kind of maintain the polymerization process once the film has been established on the surface. And then ideally that would then give you a low corrosion rate or no effect in corrosion rate, no change in corrosion rate based on using a high concentration. So this technique's patented by Schlumberger, and their sort of aim is to take this approach and optimize it to change how we protect carbon steel in these environments by varying the dose to achieve the sort of optimum conditions. So what the preliminary sort of way to establish whether or not this was going to be an effective technique was done by Evgeny and Trevor at Schlumberger, essentially using a rotating cylinder electrode and using 2 different beakers containing the different concentrations of corrosion inhibitor. So essentially what they would do is mount the carbon steel coupon on the rotating cylinder electrode shaft, immerse that in a high inhibitor concentration solution for the film forming stage. Complete that for 1 hour, and then move the RCE into another beaker with a lower concentration of inhibitor. And that period, which would be the film maintenance stage, would last for a significantly longer period. And the corrosion rates would be evaluated over that time period to see whether or not that influenced the inhibition efficiency over the duration of the matrix acidizing kind of injection period. So just to give some of their results. So what they found when we completed static tests in 4 molar hydrochloric acid at 80 degrees C with HS80 carbon steel was that the film forming stage dramatically reduced the corrosion rates. And then depending on the amount of inhibitor used in the film maintenance stage and the second stage, varying degrees of protection could be achieved. So without inhibitor, it wasn't effective. There needed to be at least some inhibitor in there to maintain the film. And obviously increasing the concentration of inhibitor resulted in better performance from the staged approach. But the key thing here is that the film maintenance stage concentration was significantly lower than the concentration in the film forming stage, which was 0.28%. So considerable difference in the inhibitor concentration that was used in those different stages. So quite a dramatic reduction in the corrosion inhibitor used, in concentration used. Introducing flow into that, and in laminar flow and turbulent flow conditions, so depending on the rotational speed of the RCE. The staged approach, which is the blue and red lines, was still effective in the different flow conditions. But when comparing to lines 3 and 4, which were control tests, so they were done at a fixed concentration of 0.01 weight%. And in this case, it's comparing with the film forming stage at 0.2 weight%, followed by 0.01 weight% film maintenance stage concentration. You can see the sort of dramatic difference between the inhibitor efficiency and the low corrosion rates just by simply having that film forming stage initially, which has a dramatic influence on ensuring that the protective film is formed, and then the film is maintained by much lower corrosion, much lower concentration of inhibitor. Whereas for lines 3 and 4, where that initial film forming stage wasn't applied, the corrosion rates are much higher because the initial film that formed wasn't essentially protective enough for the experiments that were for the duration of that experiment. So whilst these experiments were good, they showed a lot of potential for the stage approach. There was a couple of uncertainties just as a result of the method. So firstly, if you're transferring the sample from one beaker to another, you're exposing the coupon to air, the carbon steel coupon to air, and critically, also exposing the inhibitor film to air as well. Now that's quite important typically with corrosion inhibitors. When you have a film that's formed on the surface, if that's exposed to air, exposed to oxygen, it can sometimes fundamentally change the film that is formed on the surface, which introduces obviously some uncertainty in this particular test methodology. During those experiments, the open circuit potential was tracked, and of particular concern was this sort of spike here in the OCP. So this is as the coupon was transferred between the beakers. that was a particular concern because that kind of, again, implied that some sort of uncertainty or error was being introduced into the experiment. So in terms of the methodology, those were limitations. And also fundamentally, even if there wasn't a transfer process, any experiment in this environment, particularly when you're using acid, hydrochloric acid, which provide the corrosive species that would be consumed in any corrosion reactions at the surface of the carbon steel. Those species would be consumed during the experiment, so the strength of the acid and the potential for corrosion at the start of the experiment would be considerably different for several hours down the line into that experiment as the species are consumed and the chemistry within that environment changes. Similarly, the corrosion inhibitor is also used up and changes essentially the availability of inhibitor within the beaker that those experiments are completed in. So we would term that to be a closed system, essentially being that those the species, the molecules are not replenished. And if you were to consider, a pipe flow environment, that wouldn't be representative of or realistic of the environment that would be seen in the field, where you obviously got a continuous flow of a particular fluid, which will have essentially the same sort of chemistry flowing across the carbon steel pipe or tubing, whatever, at any given time during the injection procedure. So essentially, we wanted to use, or somebody wanted to use a method that wasn't affected by these issues. So that's where our flow cell comes in. So this is the cell, and this has been developed at University of Leeds for a number of years now. And we've used flow cells for various different things, but essentially, so for those that are completely unfamiliar with flow cells, they're essentially a small device that we use, which we would mount in this case, it's a carbon steel coupon within the cell. We create some sort of flow channel across. This is a top view looking above the gasket layer. We create a flow channel for the corrosive fluid to flow across in through the cell and out through the cell, out of the cell, essentially to provide an environment where we have really sort of high precision, high control corrosion experiments. So just to run through the sort of main components of those, we've got two hard layers, if you like. So they're polymer material. In this particular case, we've used an acid-resistant polymer so that we can obviously don't degrade the cell as we're running the experiments. And within those two layers, we house the electrodes for electrochemical measurements. So in the top layer, we've got a combination reference and counter electrode. And in the bottom layer, we've got our carbon steel sample, which we embed in a acid-resistant resin. We would grind that surface once we've set the coupon within the cell, so that we've got a perfectly smooth flow path for the fluid to flow across. And then in between that, we have a gasket. So the gasket is mainly used to seal the flow cell and to channel the fluid flow across the coupon. So once we seal that together, we essentially create a very controllable environment. As I said, where the fluid will flow into the cell. The corrosion reactions will be happening, the inhibition process is happening all within this particular environment. And we get some very precise electrochemical measurements because we've got ideal environment for that by placing the electrodes very close together. So just to give you an idea of the size of this, so this coupon, so this is all to scale. This coupon is 10 mil by 10 mil. So the whole device is fairly small, which is convenient for lab experiments. Using this was consider sort of flow loop, pipe flow experiments with much more difficult to fit into a laboratory environment, not as controllable. This is a very convenient way of doing some controlled experiments. And it essentially overcomes a lot of the challenges that were faced by doing these experiments using a rotating cylinder electrode or static glass beaker tests. So the advantages, as I've said, is that we've got well-defined hydrodynamics. That's useful. At the moment, we're limited to doing laminar flow experiments. It's a very low flow rate. But the key thing is that we get a consistent flow pattern across the surface, so we aren't introducing anything as a result of the experiment that could potentially influence the corrosion that we would see as a result of some sort of hydrodynamic influence or the transport of any corrosive species to the carbon steel surface. And this is some computational fluid dynamics modeling that we did a few years ago now, where we predicted the fluid flow velocity essentially over the carbon steel coupon through that gasket shape. And this gasket is a particular shape, so it's an eye-shaped gasket. So other research we've done at University of Leeds, it's not by myself, but another researcher at the University of Leeds. He's looked at the most ideal designs, flow designs for flow cells, so that you avoid any sort of recirculation. And recirculation would be bad because you can end up with sort of areas where you trap in fluid. It won't necessarily flow through the cell very well. And the eye-shaped design is good because it's got smooth edges and it channels the flow. It widens over the coupon, which we've represented by this box here, so that you get a consistent flow pattern across the sample. So essentially, the color scheme here represents the velocity across velocity of the fluid at each of these points within the cell. And as you can see, it's a fairly consistent blue color across the sample, which means we essentially got a very consistent flow pattern across the sample. So that's important because you don't want any variation at different points within the regions of that sample. It's once through as a cell, so we would position the cell in between a beaker, which we would continuously flow hydrochloric acid or whatever electrolyte we'd want into the cell, which means that we're constantly replenishing hydrochloric acid and acid corrosion inhibitors. So the concentration flowing into that cell is never influenced by the corrosion processes. We can do the electrochemical measurements. It's obviously very useful to determine mechanisms, corrosion rates in situ. For other flow cells that we've designed, we've also been able to do kind of in situ imaging and X-ray scanning to understand when corrosion product layers are forming on the surfaces in situ. So they're very useful technique for a number of different applications. And also pretty useful in this test is that we could have seamless changes in conditions. So simply by moving the tube into different containers of fluid, we could very easily change conditions in the cell without exposing the coupon to air. So that was the plan then with Schlumberger. So as I said, they've got to this point where they developed the idea. We have a technology at the University of Leeds, which is kind of ideally suited to studying this. So we completed the research collaboratively using what's called an impact acceleration account. So this is funded by the Engineering and Physical Sciences Research Council, which is one of the main UK funders for corrosion research. And these particular accounts grants are quite unique in that they focus on impact acceleration. So the idea is not to be fundamental research, but it's to bring these research ideas at a reasonable sort of technological level and establish their application in the field, in industry, and whatever application that may be. And that was our idea with Schlumberger, was to evaluate the staged approach, so we could provide some further evaluation of the technique prior to its application in industry. So to give you an overview of the methodology, so we looked at two different carbon steels. So we've got HS80, which would be the coiled tubing material, and N80 carbon steel, which would be common as the casing material. You can see you've got various different compositions of those two steels and slightly different microstructures. And obviously it's important to evaluate both of those. Like I said, the acid is exposed to any sort of materials in that environment during the matrix acidizing procedure. So we need to know how effective it is, how effective the inhibition methodology is, not just on, on some metals, and as many as we can kind of characterize as possible. So we did these experiments at 80 degrees C using 4 molar hydrochloric acid, and all at a flow rate of 5 milliliters per minute. So this would give laminar flow conditions, essentially so that we limit the limitation of using the flow cell, but also it gives us a controlled environment, and we're not necessarily looking at how hydrodynamics influence conditions in this particular study. So as I said, we do electrochemical measurements, and we'd use the carbon steel coupon as the working electrode. We'd use a silver chloride reference electrode and a platinum counter electrode to complete the electrochemical cell. And to assess how effective the inhibitor is, we would complete linear polarization resistance measurements every 15 minutes. So one of the challenges with LPR measurements and any electrochemical measurements in such a high strength acid environments is that the currents are so extreme that if you polarize too excessively, particularly when you've got an inhibitor film, you can fundamentally change the properties of that film by the electrochemical measurements that you're completing. So we deliberately scanned over a very narrow range relative to OCP. So -5 millivolts to +- millivolts relative to the open circuit potential, so that we didn't influence any measurements. It didn't influence the film as a result of any of the measurements we completed. And we used a polymerizable inhibitor, one of Schlumberger's inhibitors, to evaluate how effective this inhibition technique was using our flow cell. So there's 2 types of experiment that we completed. So we have a control experiment, which is where we have a fixed inhibitor concentration. So this isn't a staged approach experiment. It would just be a consistent inhibitor concentration for 4 hours. And these are the 4 concentrations that we used. And what we would do, we would prepare the carbon steel coupon, mount it within the cell, seal it in with the resin, grind the sample to get the surface finish and smoothness of the whole cell, flushness of the sample sorted before we would seal it with the gasket, fasten it together with bolts, and then we'd immerse it in a water bath. So this was set to 85 degrees C to account for the heat transfer into the cell and into the tubing, and we validated this previously with by using a thermocouple positioning where we would fit the sample. So what we would do, we would prepare a solution in a beaker of 4 molar hydrochloric acid. We would add the corrosion inhibitor to the acid, use a peristaltic pump to pump the solution through some acid resistant tubing, which would be immersed into the water bath and flow through the flow cell and then out into a waste stream. For staged experiments, these are slightly more complicated, but essentially using the same equipment, same technique. So for these particular experiments, we had a film forming stage where we had 0.28% of the corrosion inhibitor for 1 hour, which was followed by a film maintenance stage for 3 hours. And that was using a lower inhibitor concentration. And these are the 3 concentrations we used, which were the same as the control experiments. So in this particular case, we've now added a second beaker in there. So for the first stage, we would have the 4 molar hydrochloric acid, 0.28% solution. We'd have the tubing, again, pumping, using a peristaltic pump the solution through and into the waste. After 1 hour, we would switch the pump off We'd remove the tubing and wipe any sort of remaining acid off the surface of the tube, immerse it into the stage 2 beaker, which would contain the same hydrochloric acid, but a lower inhibitor concentration. And then we would restart the pump. So that whole process was very quick. It took approximately 20 seconds to do that, which is much quicker than the transfer process with the RCE. But fundamentally, by stopping the pump, there's no stage with any air get into the system. So it'd be a continuous contact with the inhibitor and hydrochloric acid solution. So these are some of the results that we've got. And what these results are showing is essentially our polarization resistance over the 4-hour experimental period. So what we've done here is plot the results as 1 over RP, polarization resistance from the LPR measurements, rather than plotting the corrosion rates. So the reason for doing this is that it can be tricky to calculate a corrosion rate from an LPR measurement at times. It's not always scientifically accurate. For those familiar with electrochemical measurements to know about measuring Tafel constants to correct the corrosion rate value you get, becomes quite challenging in an inhibitor environment. Not necessarily sure whether or not your Tafel constants will change throughout the experiment. So it can be quite difficult to essentially say you have got this 1 Tafel constant for the 4-hour duration and therefore a certain corrosion rate in millimeters per year. But 1 over the polarization is directly proportional to corrosion rate. So in this particular case, when you plot 1 over RP, the trend you would see would be exactly the same if this was shown as a corrosion rate. But we're just not introducing those sort of uncertainty that we would get as a result of making those corrosion rate calculations and Tafel analysis. But just to give you an idea of how effective the inhibitor has been in terms of corrosion rates you might expect, the pink line here, which is the 0.005 weight percent, so the lowest concentration we studied, essentially gradually tended towards 1. So essentially 1 over an RP value of 1, which becomes essentially the limitation of what we can physically measure in this particular with this particular technique, because the currents are so extreme, and the other resistances that are present in the solution become significant in the measurement. So essentially this 0.005 weight percent in inhibitor concentration for HS80 over that test duration provided no real inhibition at all, and the corrosion rates were extremely high. But as you can see, and as you might expect, you increase the inhibitor concentration, the corrosion rate 1 over RP decreases, and it becomes more efficient. For N80, similarly, increasing concentration was more effective. But generally, the corrosion rates are quite higher on N80 due to the sort of microstructural differences between the steel, between the two steels. So what essentially that told us was that the critical component in this is the N80 carbon steel. That's going to suffer more corrosion. The inhibitor concentrations aren't as effective. Therefore, this is kind of like the critical component for evaluating the staged approach. So we moved on to the stage experiment. So like I said, we would have the film forming stage for 1 hour, switch the tube into the low concentration, and then we'd continue the film maintenance stage for the different inhibitor concentrations and the much lower inhibitor concentrations than during this stage. So during this period, so obviously we've got 3 different lines on this graph, but during the first hour, all the inhibitor concentrations are exactly the same. But beyond that period, then we have the different concentrations which are listed here. And what you can see for the HS80 is that the inhibition efficiency still remains fairly high during that period. and we don't see a dramatic increase in corrosion rate. The film formed on the surface remains persistent. Towards the end of the test, we start seeing some change, but no dramatic increases in corrosion rate. On the N80, however, and that I should point out as well, that's obviously for these inhibitor concentrations, which I just showed you, so the 0.005 weight percent, blue line here, is maintaining some pretty high levels of efficiency. And when you compare that to the slide I just showed you, where essentially there's no inhibition, it shows you just how critical the film forming stage is. This concentration wasn't really effective on N80. We started to see the corrosion rate increasing quite dramatically in the final hour. So we decided that essentially that concentration was inadequate for corrosion protection. But it certainly showed that the staged approach can be effective once you've established an appropriate film during that first part of the exposure period. So, as I said, one of the challenges that was noticed during the rotating cylinder electrode experiments is you get this OCP spike when the coupons were transferred and exposed to oxygen, which we don't see in the flow cell experiments. This is the flow cell experiments on the left. As we change this is just for the red line, and the black line is a control test where there is no changing of tubing. It's just a consistent exposure to 0.2 weight percent. You can see that there's no significant changes. We do see a kind of slight change, but not the same spike. And it's likely that change is just because of the fact that the inhibitor concentration has changed rather than some fundamental difference. And we didn't notice any sort of dramatic changes in these conditions either, which if you look at the RC experiments, there's some more sort of dramatic differences in the OCP after that initial period. So it kind of gave us some validation to say that our technique was effective for these particular conditions. So we chose to continue with the 0.01% as being our optimal dose, and essentially to, well, not necessarily optimize in these conditions, but in terms of the conditions that we studied, that would be the minimum dose that we required. So we chose this to take this further forward to do some further analysis. And this slide just sort of compares the corrosion efficiency, essentially inhibition efficiency of the staged approach. So this is just the blue line only. When you compare the black line, which is the control at 0.28%, and the control at 0.01 weight percent. So you can see there's a dramatic increase in efficiency of the inhibitor compared to the 0.01% control test, showing that, again, by performing that film in the initial stage, the lower concentration could still maintain good inhibition and efficiency. And the values that we've reached at this stage are within sort of acceptable values for what Schlumberger would deem as acceptable corrosion inhibition efficiency in this particular environment. This is even more dramatic for N80, where at 0.01% for the control experiment, inhibition efficiency was quite poor and corrosion rates were quite extreme by the end of the experiment. But again, that film forming stage was able to maintain, or was able to provide a persistent enough film that could be maintained with a much lower concentration of inhibitor efficiency. And the difference compared to continuing with the 0.2 weight percent film is not necessarily sufficient enough to justify the increased concentration throughout the entire experiment. So reducing the inhibitor concentration during the film maintenance stage is particularly effective and significantly reduces the corrosion inhibitor consumption as well. So inevitably, idealized sort of laboratory experiments always come with some sort of limitations, and then applying this in the field always has some sort of or various different parameters that you can't necessarily account for as easily in a controlled environment in a laboratory experiment. But one of the key things was understanding the influence of pre-corrosion. So the experiments that I've shown you to date, so far, were all completed on a polished sample, controllable surface finish, with no sort of layers present on that surface, which is great for experimental control, but obviously is not necessarily what would be seen in reality in the field. So what we did was introduce a pre-corrosion period. So we exposed the carbon steel to uninhibited hydrochloric acid for a 10-minute period. That allowed the carbon steel coupon to corrode. It influenced the surface that essentially would be exposed to the inhibitor once the flow of inhibitor starts in that system. So as a comparison, so this on the left, so we've got again, comparing at the 0.01 weight percent staged test. So we've got 0.2 weight percent during the film forming stage again, 0.1 weight, 0.01 weight percent during the film maintenance stage for the following 3 hours. And you can see, so for the black line, this was the wet ground surface, so there's no pre-corrosion. There wasn't a dramatic difference once we did introduce some sort of pre-corrosion. The corrosion rate was slightly higher, but generally the inhibitor was still able to protect the carbon steel quite effectively. N80, on the other hand, again, as I said at the start, is generally the limiting factor in the success of this approach. We saw some pretty dramatic increases in corrosion rate on the pre-corroded samples, so the blue line. So that sample had been pre-corroded. It changed the sort of properties of that surface, and the inhibitor was much less effective once we switched to the film maintenance stage, and we couldn't physically protect the surface as we wanted anymore. So the causes of this was essentially that we noticed more sort of localized corrosion effects on that surface and a much rougher surface after the N80 was exposed to 10 minutes of hydrochloric acid. So what we did was just complete a 10-minute experiment, expose the steel to the uninhibited hydrochloric acid, take those samples out and do some surface analysis on those. So this is some surface analysis using a white light interferometer. It builds up a 3D scan of the carbon steel coupons after they've been exposed to that environment. And we've got a scale here. It might not necessarily be that clear on the images, but essentially the more consistent color, the more even that surface is. There's fewer sort of variations in the surface profile. And what we saw on the N80 sample, there was that you might be able to see the sort of the darker bluer areas in that sample. So there's a band running across here as well. A few other areas. We noticed that essentially there was a lot more localized corrosion effects on that surface. And purely if you just look at the scale with which this goes down to, got some fairly deep sort of, not necessarily pits, but sort of pit-like features within that surface. Essentially, this is giving us the theory that either there's some sort of effect happening, which is detracting from the inhibitor performance within those sort of localized regions of attack, but also that we've got a significantly rougher surface, which can translate into essentially being a higher surface area for which the inhibitor would have to protect. So essentially all of those parameters contributed to the reduced inhibition efficiency of the stage approach on the N80 coupon. So what we did as a solution, and this is kind of one of the convenient things of this test methodology and the staged approach, is that by varying the film form stage concentration, we could increase the concentration during this stage so that we could protect the steel more effectively. So what we did was increase the film forming stage, stage 1, concentration to 0.5 weight%. So this is the red line here. While still maintaining a 0.01% stage 2. And what we saw again was much more acceptable corrosion rates. We didn't see as significant an increase at the end. So essentially what that told us is that by varying and optimizing the inhibitor doses, we can account for some more sort of variations that we might see in different field conditions. So that's all the results we've got. So to kind of conclude, we've shown that the stage approach can be very effective, and the key thing is to establish an effective film during that film forming stage, and then we can maintain that film with a much lower concentration during the second stage. We can see significant inhibitor reductions, concentration reductions to maintain a protective film. We do see some effects of pre-corrosion, and optimization of the dosage can influence how significant that can be. I propose sort of plan for the future of this is, again, like I said, this isn't fully optimized in terms of concentrations. Inevitably, when this is used in the field, those concentrations would vary slightly again, depending on the application, but there is potential to optimize this. And there are plans to do field trials eventually. Schlumberger are planning to do, taking this technique to see how effective it works in the field. In terms of the research we do at Leeds, we are interested in sort of other corrosion inhibitors and acid corrosion inhibitors in different applications, just to understand if this film persistency sort of theory applies perhaps more widely than just in the conditions we've studied that I've shown today. And also we're hoping to kind of develop the cell to be able to extend the analysis into more turbulent flow conditions, introduces some more severe hydrodynamic conditions, so that we still get the control of a flow cell, but can introduce the hydrodynamic conditions that obviously we can't yet study, which would be perhaps more relevant to the field. So yeah, thanks very much for listening. Thanks obviously to Schlumberger and the EPSRC who funded this research. If there's any further questions, so I've seen some questions have been added in the Q&A, but if there is any questions or you want to get in touch to discuss some of these projects and the potential sort of collaborations that we can do at the university, my contact email address is there, and Rick Barker, my line manager, supervisor of this work, and obviously as well, you can feel free to contact Evgeny as well, who'd be more relevant in the industrial aspects of the application. So yeah, thanks very much.
Thank you very much for that presentation, Joshua. It's very detailed and appears to be well received. So we've got lots of questions to go through now. So just start at the top. First question comes from, apologize if I butcher your name, Musin Al-Haddad. Have you tested the corrosion inhibitor with HCR 6000 acid system?
No, I'm not sure what that's referring to.
So Josh, can I answer this question?
Yeah, go on. Yeah, more relevant to Evgeny. Yeah, go on.
Oh, it's definitely not tested, but my question, what is the composition of the system? Is it methyl sulfonic acid? And if you yeah, do you know what is the composition of this specific system?
I don't think we have those details available. This may be one for further investigation. Perhaps we can provide an answer for that at a later date. Okay, we'll move on. Next question, again, how can you explain the increase in corrosion rate in slide 12, though the increase in corrosion inhibitor is known to enhance protection, i.e. film stability?
So I'm on slide 12, so this is the corrosion potential rather than corrosion rate. So I don't know if that's I don't know if that's what it's referring to, but what have we got? Something for the increase in
for this specific system, corrosion of course will drop with corrosion inhibitors concentration. Yes, it's just corrosion potential.
Yeah,
What's shown on this picture.
Yeah, so again, the very concentration has an influence on corrosion potential. Depending on the type of inhibitor used, it can fluctuate either anodically or could stay the same in some conditions. Generally, the high concentration that we use shift it more anodically in this case, but also it depends how effective the inhibitor actually is in that environment as well.
Okay, thanks for that. Next question, are you planning to test the impact of propant on the inhibitor efficiency?
Not as part of this research, but maybe Evgeny, is that something?
Yes, not clear for me again, like what is, why we need to test propant, because propant is used for fracturing, but matrix acidizing usually not used propant because it's a great channel and propant not required to, it's part of process. But usually propant is sand, just river sand or maybe some ceramic materials, and I would expect no interactions with metal or with acids or inhibitors. So it means there will be no impact of propant on inhibitor performance and corrosion.
Okay, thank you very much for that clarification. Next question we have is from Frank Chen. The question is the polymerized inhibitor film conductive to enable LPR measurements? The flow speed in the test is very slow. How is an accelerated fluid flow to achieve a stable corrosion system? Yeah.
Can I answer the question as well? So
yeah, go for it.
So first answer, so the thickness of this film, polymeric film, is very, very minor. It's about few nanometers, maybe 10 nanometers. So it's very conductive. So it's no problem with corrosion measurements, but concerning the flow speed. So in our corrosion science paper, we published like several papers on investigation effect of flow on corrosion for the acidizing conditions. And actually, when we conduct RC, rotating cylinder electrode at speed 6,000 RPM, the flow conditions, it means yield, wall shear stress and Reynolds number is very similar to performance of in real cold tubing applications. For example, when we pump 2 barrels acid in minutes via cold tubing about 1 inch diameter. So it's real high turbulent flow conditions. And we actually investigated under these highly turbulent flow conditions. It was presented in some slides on Josh's presentation.
Oh, thanks again for that answer.
And in terms of the flow cells, so as I said, they are very limited to low flow rates. But one of the things that we are looking at the minute is trying to introduce essentially more transfer of species within the flow cell environment. It is challenging to get a sort of controllable environment in that case. But we believe we've got a few sort of techniques, a few possibilities where we can extend this to include some different or more aggressive hydrodynamic parameters. And we will see kind of, I guess, how effective that can be. But that's something a little bit further down the line in terms of technological development.
Okay, excellent. Okay, just a couple more questions on corrosion rate. So we've got 3 in a row. So the first one is, in the corrosion rate analysis, did you consider or see pitting? What was the acceptance criteria?
So yeah, that was something that we didn't look into in this particular case. From the surface analysis we completed, we showed that there was a little bit more, I guess, what would be considered pitting or pit-like features as a result of the exposure to the acid without any inhibitor. Our kind of, I guess, theory in this point would be that we want the inhibitor to be so protective that we wouldn't see any uniform corrosion or localized corrosion. And for the HS80 steel, we didn't notice any particular pit-like features anyway either, even when it was exposed to the pure or the concentrated hydrochloric acid without corrosion inhibitor. Evgeny, I don't know if you've noticed any sort of significant pitting before. Have you done pitting experiments in other studies?
Yeah, good. So according to internal standards, the pitting index for all matrix acidizing should be 0. or 1, which is actually very minor, actually no real pitchings. So it's standard. It means actually it's issue with this technology, because this technology is not really can be easily evaluated by standard methodology for which acceptable in the field, all clients. For example, corrosion rate should be measured, if not corrosion, in millimeters per year, or resistance is measured in pounds per square foot. And corrosion is independent on time. So it will be equal number 0.05 pounds per square foot for independently and length of acidizing job. It might be 3 hours, might be 6, might be 12 hours. Corrosion will be still 0.05 pounds per square foot. And pitting index will be also should be 1 or 0. Actually, no pits on main surface. It's only with some minor, very minor, not pitting, just some some texture on the edge of standard coupon test. And probably in the chemistry is also demonstrated, so the pitting is very negligible, or no pittings. It's only developed surface, rough surface, what we found.
Well, thank you very much for that. Okay, next question. You see you're already there, Joshua. It says, on slide 20, corrosion rate is increasing after 4 hours. Have you tried to test it for more than that? Example 12 or 24, since actual stimulation can go for more than 6 hours usually.
So in these tests, we just did 4 hours. Yeah, there is, in some cases, there is a minor increase. Evgeny has done work over longer periods, over 6 hours. In the particular case, kind of interest would be that the injection period would be up to 6 hours, and then it would become a flowback challenge. And as I said, some of the work that Evgeny had done previously with University of Leeds, where we looked at the flowback effects, and we completed experiments over, I think there were 24 hours with Evgeny, with Ben, and we looked at the kind of the effects of how the acid concentration changed over that period, and corrosion rates that we measured using the same or similar acid corrosion inhibitors. I think also, Evgeny, I think the theory would be to, is it to increase in inhibitor concentration again during that flow period? Flowback period, sorry.
Yes, of course, like we are not, so answer yes, of course, we analyzed at a longer period of time. And also analyzed, for this next question, analyzed at high temperature up to 250 Fahrenheit. So it means it's temperature in times, acid concentration, everything analyzed. It probably is the best way to find this answer in our patent, because it's patent quite well written. So yes, of course, analyzed. Yes. And results quite positive.
Oh, that's good to know. Okay, next, I think there's 2 small questions from Nivedita. So the first is 1,000 millimeters a year corrosion rate was considered for some experiments in your slides. Was this practically observed? And the next one is, for temperatures above 85 degrees, can the ACL be applicable?
So yeah, we've validated the electrochemical measurements with mass loss experiments in the past as well, which have shown so much mass loss that it would be equivalent to around of the order of 1,000 millimeters per year. So yeah, it is a pretty extreme corrosion rates that you get in an uninhibited system. Evgeny is for the higher temperatures. I think some acid corrosion inhibitors don't function as well, I guess, do they? Yeah, as the temperatures go above 100 degrees, but I don't know whether Evgeny has got experience of this particular inhibitor at higher temperatures.
Yes, it's, yeah, even at ATC, the corrosion 1000 is so significant that you might issue with coupon dissolved during your experiment. Especially at high temperature, yes, you can lose coupon during the experiment, so you will never actually investigate for real life corrosion in uninhibited acid. For research purposes, of course, we need to know in order to investigate inhibitor efficiency, we need to know about the corrosion of uninhibited acid. It's very high. It's from 7 to 100 to 1,000 liters per year. It's not surprised us. So it also depends on acid concentration. So yeah, it's very normal. And actually, corrosion rate nearly exponentially increased with temperature, and same nearly exponentially increased with acid concentrations, despite of some rule.
Okay, thanks for that. Next question we have is from Chris Coogan. So it's a long one, so bear with me. So I guess the first part of it is just talking about the limitations of LPR probes. So it starts, thanks for your talk. I note that you use low field LPR for your flow cell corrosion rate determinations. The LPR approximations only hold if there are no electrochemical oxidation or reduction processes occurring in the system. This assumption may not hold if you're using an inhibitor which is electropolymerizing, a film-forming inhibitor. Have you considered swapping LPR for electrochemical impedance spectroscopy with a view to decoupling the corrosion and polymerization responses?
Yeah, so and that's one of the, I guess, the challenges of any electrochemical measurements with inhibitors or whatever essentially is formed on the surface. That LPR doesn't always tell you exactly what you're expecting it to do, or how it's interpreted. I think one of the main challenges with it being such an aggressive environment is the duration over which you'd be polarizing for, I guess, with impedance spectroscopy. It would be interesting to look at to see whether or not we could actually identify the different sort of mechanisms that are occurring. It would be particularly challenging in I guess, in the flow cell environment, because purely from the duration of the measurement that would be completed. Take between 10 and 15 minutes to do a full impedance scan, which in a flow environment, I guess, might not be as helpful. But I don't know whether, again, Evgeny, I don't know if you've done any impedance studies on in other tests, in RCE tests or in static tests with these inhibitors.
I think it's very interesting question. So it's very interesting from research perspective. First, like what we need for analysis, we need a method which minimized impact on system. When we use polymerizable inhibitors, what is happening when we start polarizing anodic polarization, even 5 millivolts in anodic direction, you'll start very strong corrosion. Inhibitors start to desorb because you lost metal. It means you lost bonding between polymer film and metal. So why we try to minimize impact of our measurements. We use LPR very periodically, maybe only 20 minutes. But even this might affect on adhesion of inhibitor film to surface. So it means if instead of LPR use TAFL, it might be end of experiment, because TAFL definitely during strong polarization change surface significantly. Corrosion potential will take 10 minutes, for example, to back to normal OCP. If you used impedance, of course, it's also possible. They investigate impedance, but it's also long exposure on system. It might be case when you, during experiment, you also change your system. And you should exclude this impact.
Well, thanks for that. So we just have one clarification. So we just got a comment here, not necessarily a question, and it's an interesting presentation, but curious how the test probe scale would compare to real life industry application / scenarios. I guess that's always going to be a question we get. How does academic research flow into industry? Any thoughts on that at all?
Yeah, I guess in this, obviously, yeah, it's difficult to imagine how a very sort of controlled small experiment actually translates into a much bigger application with a lot more variation in that. I think what we're always trying to establish is what the worst case scenario would be, which is probably what we've shown with the sort of pre-corrosion. We're exposing it to 10 minutes of high strength acid, things like that. But obviously, without any sort of field data, field trials, we essentially don't know. But we don't know how effective it would be. But we've essentially created enough sort of scientific evidence at this stage to say that this could work in practice, and there's very strong evidence to suggest that it would. Evgeny will probably be able to comment on more on sort of translating things into the field. A lot of what Evgeny's research would be to directly use a lot of the same techniques that we would use in academia, but physically translate those into the field. So yeah, if you've got anything to add, Evgeny.
Yes, actually plan to implement this technology via field trial in 2020. Yes, and you know what is happening. So, and we still not really planning to field test due to some issues. So, but everything is ready for, we find actually good customers in Saudi Arabia and Qatar for field test. Conditions will be quite mild. Temperature 80 C, which is very typical in Saudi Arabia. Conditions will be 15% acid, all known chemistry, metals, metallurgy. So it means it's everything is ready for field trial, but now some delay, unfortunately.
Well, fingers crossed that gets done in the near future. It'll be good to get those results through.
Yes, and SPE we published it or presented in Aberdeen last year on Corrosion conference. Yeah, we actually describe a different scenario of implementation of this technology from low to which is has minimum impact on client's cold tubing. It means it can increase lifetime, but minimize some potential damage. Step by step from low risk to high risk scenarios. It's all defined, and just wait for better COVID situation.
Thank you very much for that. I think we just got one more in the system. So last question. The impact of chlorides. Are you planning to test its impact, since chlorides can impact persistency of inhibitor film?
I guess we've got a quite high chloride environment in the high strength hydrochloric acid. So I think the hydrochloric acid environment would probably have the most critical influence on any corrosion mechanisms and inhibitor mechanisms.
Probably already working with quite high chloride concentration if Cl is chloride, not corrosion inhibitor. So, but usually, so when people mix some two stuff, when you investigate corrosion in a production environment, in or drilling fluids, when you increase concentration of chloride, you actually would expect some decrease in corrosion due to some impact of oxygen, because at high chloride concentration, less oxygen dissolved. It will be strong effect on drop in corrosion. But in our environment, so oxygen is present, and we're already working at very high 4 molar, even higher concentration. Even 28% is much higher than 4 molar acid HCl.
Okay, thank you very much. So that's everyone. I'd like to thank everyone for asking a question tonight, and thank you for presenting a very interesting presentation. I'll hand it back to Herman. Thanks again.
Thank you very much, Dr. Oli, for taking the questions, and thanks for our presenters today for this excellent presentation, which raised a lot of questions. And thanks everyone for taking the time attending today, and apologies for going a little bit over time, which is expected when you have a very interesting topic and a lot of questions. Just to remind you that when you're leaving the webinar, there will be a short survey. If you need a CPT certificate, please make sure to fill the survey and respond to the CPT question as yes, and include your email address. And also for the presenting in the future events, if you are interested, put your contact details and the topic that you want to present in the survey as well. And as I mentioned, the slides, the question and answers, and the recording will be available on the website and the YouTube channel for your future reference, or you want to share with your contacts. Our next presentation will be on 22nd of February by Intertech, and the topic is implementation of plan, do, check, act, review of an offshore oil and gas operator's corrosion management policy. Thanks again, and have a good rest of the day or evening.